Good morning, Masood. How are you, sir?
Good morning, Dr. Sibert. How are you? I'm fine.
Doing well, thank you. Morning, Joe. Morning. Okay, I've got 2 minutes past the hour, so why don't we go ahead and get started. For once, I don't think I have anything new in the way of housekeeping or logistics to discuss. Do you guys have any questions or concerns that you want to bring up before we get started with physics for today?
Homeworks are due the 29th.
Next Friday, which I think is the 30th. Okay. Yeah, homework cutoff next Friday, the 30th. I intend to write and post the second midterm online this Friday, and I will give you guys until the last Friday before the final exam week, which is, I guess, 2 weeks to complete it. I don't intend it to take you that long. I'm just trying to give you some extra flexibility so that I don't have to cut off homework submissions until the end of next Friday. And if you're still stuck on something, then after that, you will have homework solutions available to you to help you solve any problems that you're stuck on. Any other housekeeping business before we get started with identical particles today? Okay, it doesn't sound like it. So I think at this point, we've finished the main storyline of the semester up through time-dependent perturbation theory, scattering theory, and all of that jazz. The phase shifts and angular momentum states were probably the end point of that discussion. So now we're circling back around to pick up any specific topics, special things that we missed out on before. And all of this, I think, kind of fits into the framework of how to go beyond single particle quantum mechanics, or maybe a couple of particle quantum mechanics, things that will eventually lead us to needing fully fledged quantum field theory. So the topic for today is identical particles, which is going to lead us into a discussion about symmetry and anti-symmetry of bosons and fermions. The cornerstone of this is something that we talked about back at the very beginning of the semester when we discussed spin. When we enumerated the types of spin that particles can have, we found that half-integer spin particles, which we call fermions, had very strange properties under rotation. We showed explicitly that for a spin 1/2 particle, that if you take it and you rotate it by 1 full revolution, which is a rotation of 2 pi about any axis, that the thing actually doesn't map back onto itself. It maps back onto itself with a minus sign. That minus sign is going to come back for us today in a very big way, and that's going to lead ultimately to the Pauli exclusion principle. So let's take a second and remember how this came about. We found this by taking a spin rotation, the unitary operator that rotates spin by an angle theta equals 2 pi about some arbitrary unit vector n. And we're rotating a 2-component spinner, although in this case, this applies also for any half-integer spin. So we write down what is that spin rotation operator. This is e to the minus I over h bar, spin dot the rotation angle theta, which is 2 pi n, psi plus, psi minus. The spin operator is given by the Pauli matrices. It's h bar over 2 sigma. So this gives e to the minus I pi sigma dot n, where the sigma are the Pauli matrices. Psi plus, psi minus, and you guys got exhaustive process on rotation operators like this on the first midterm. And we now know that you should definitely expand this thing in a form that looks like Euler's formula, or you would write this as cosine of the angle pi times the unit matrix 1 minus I sine of pi times the Pauli matrix combination sigma dot n. All of this is the rotation matrix that acts on psi plus and psi minus. And for the particular case where the rotation angle was 2 pi, I get cosine of pi, which is -1, sine of pi is 0. So it doesn't depend on n at all. That drops out completely, and I just get this minus sign. And so I get minus psi plus psi minus. So rotation on 2 pi about any axis of a spin 1/2 particle changes its sign. And so this is going to give us the property of anti-symmetry under rotations. A complete proof of how this connects to the symmetry and statistics of the particle is beyond the scope of quantum mechanics. You really need quantum field theory to derive it, but it goes by the name of the spin statistics theorem. And even if I can't prove it to you with the machinery that we have available now, I'll try to motivate it a little bit in a few minutes when we get there. So for our purposes, let's start by defining an operator that exchanges two different particles, and we'll talk about the implications of a symmetry of your exchange of particles. So let's consider a two-particle system. In a state, all right, psi 1, psi 2, where I don't particularly care what the quantum numbers psi 1 and psi 2 are referring to, just that this first entry is telling me about particle number 1. Particle number 1 in state psi 1. And this one is telling me that particle number 2 is in state psi 2. These could be levels of the harmonic oscillator. They could be NLM states of the hydrogen atom. None of that particularly matters for this discussion. What we want to do is we want to define an operator that switches which particle is in which state. So let's define an exchange operator. It might be better to call it a permutation operator. As something which swaps the state of the particles. So I think we've used about every letter in the alphabet at this point, so apologies if I'm recycling things. I decided to call this pi. Capital Pi is going to be my exchange or permutation operator. The definition is that the exchange operator on my state psi 1, psi 2 switches which particle is in which state. So now particle 1 is in state psi 2, particle 2 is in state psi 1. So this exchange operator has a number of particularly simple properties. It's kind of reminiscent of parity. It has the following properties. It is self-inversive. It is unitary. And it is also Hermitian, just like parity. And because of this, we will show momentarily that this implies that it has eigenvalues plus or minus 1. And this is what's going to define our symmetric versus anti-symmetric states. So how do I establish these properties? Self-inversive is pretty straightforward. I just look at what happens when I swap the identities twice. Clearly, if I have pi squared on the state psi 1, psi 2, after I hit with the first exchange, then I get psi 2, psi 1. I hit it with the second one, and I get back psi 1, psi 2. So comparing the state that I start off with and the state that I end up with, I immediately see pi squared is the identity operator, and this is equivalent to saying pi is its own inverse. So that is this first property of being self-inversive. Once we've established that it's self-inversive, we'll prove unitarity and hermiticity at exactly the same time. To do that, we need to define what pi dagger is. It's been a long time since we talked about this kind of stuff, but remember that the adjoint or the dagger of an operator is defined by what it does to a complex conjugate matrix element. So imagine that I've got two of these things. So pi dagger on the particular state psi 1, psi 2, projected onto a different state, I don't know, phi 1, phi 2. The definition of adjoint means that it's the complex conjugate of the matrix element swap the other way around. Phi 1, psi 2, projection operator, phi 1, phi 2, complex conjugate. That has nothing specific to do with this operator. This is the definition of what adjoint means in the first place. It is the conjugate transpose of the matrix. So let's take a look at this in a particular basis. So suppose we work in a position basis. So consider the position basis. So let me suppose that I have R1, R2, and I want to look at pi dagger R1 prime, R2 prime. So the definition of this guy is the complex conjugate of the matrix elements swapped, R1 prime, R2 prime, exchange operator R1, R2, complex conjugate. And now let's simplify the right-hand side. The exchange operator swaps which particle is at which location. So I have R1 prime, R2 prime, R2, R1, complex conjugate. This overlap is a combination of delta functions. So particle 1 here is at position R1 prime. Over here it's at position R2. This overlap is 0 unless those are the same position. The same is true about particle number 2. So this is the complex conjugate of delta function of R1 prime minus R2. Also delta function of R2 prime minus R1. Complex conjugate. Obviously, now the complex conjugate doesn't do anything, and I can get rid of it. And so now I just want to read these delta functions back off in a way that looks like the matrix element that I started with. R1, R2, pi dagger, R1 prime, R2 prime is equal to delta function of R1 prime minus R2, delta function of R2 prime minus R1. So I'm going to read this off as R1 on the left, R2 on the left, and what are they overlapping with to give me this combination of delta functions? R1 lines up with R2 prime, R2 lines up with R1 prime. So this is equivalent to this overlap. I set it up so that the left-hand side, the bra, looks the same. And now I just write this as the swapping operator, the exchange operator on this state. So this is R1, R2, exchange operator, R1 prime, R2 prime. And now I'm done because the state on the left is the same, the state on the right is the same. And so since this is true for any state in a complete basis, these operators are equal to each other. So this is enough to show that pi dagger equals pi, which means that it's Hermitian. And if it's Hermitian and it's self-inversive, then it's automatically unitary too. So this gives me pi dagger equals pi inverse, which is Unitarian. Since pi and pi inverse are the same thing, since we already established that. Okay, great. So the exchange operator looks a lot like parity. It is self-inversive, unitary, and Hermitian. And the combination of being unitary and Hermitian at the same time guarantees that it must have eigenvalues plus or minus 1. We showed a long time ago that any unitary operator acting on some eigenstate must have eigenvalues of unit modulus. So I don't know, let me call this theta. It has to be something of the form e to the I theta. It could be a complex number, but its modulus has to be 1 because u times u dagger is equal to the identity. If it's Hermitian, then it also means that the eigenvalues are real. So then I've got e to the I theta equals e to the minus I theta. And this is enough to tell me that I must have plus or minus 1. It's something whose absolute value is equal to 1 and it's real. So there's only two choices, plus or minus 1 for the eigenvalues. Okay. Again, very much like parity. So this lets us classify the eigenstates of the exchange operator. there are exactly two options. I can have an exchange operator on a quantum state psi, and I'll call it psi s, whose eigenvalue is +1. So this is a symmetric state. You swap which particle is which, you get a plus sign. The other option is you can swap which particle is which and get a minus sign. This is the anti-symmetric state. So my simple product states, if I just take psi1, psi2, is not an eigenstate of the exchange operators. But I can make states that are symmetric or anti-symmetric by explicitly symmetrizing or anti-symmetrizing them under that exchange. So I can construct psi symmetric as 1 over root 2 psi1, psi2 plus the exchange combination psi2, psi1. And I can construct the anti-symmetric state with a relative minus sign. Psi1, psi2 minus psi2, psi1. So these are the eigenvalues of this operator. For a product combination of states, these are the eigenvectors. So the discussion around identical particles comes in when we say that if two particles are identical, then nothing changes when I swap them. That means that the exchange operator is a symmetry of the Hamiltonian. So if two particles are identical, or indistinguishable, then particle exchange is a symmetry of the Hamiltonian. So that means if I transform the Hamiltonian under exchange, I get the same thing back. How do I transform an operator under exchange? Well, I take the operator and I hit it by the transformation on the left, pi dagger, and on the right, pi. And the statement is, if this is a symmetry, then the exchange transformed Hamiltonian is equal to the original Hamiltonian that I started off with. Transformed H equals original H. And this, of course, means that the Hamiltonian and the exchange operator commute with each other. If I multiply from the left by pi, then I get H pi equals pi H. Subtract this over to the left, then this is H pi minus pi H equals 0. Of course, this is just the commutator of H with pi. So if particle exchange is a symmetry of the system, then your eigenstates of the Hamiltonian have shared eigenstates that have either symmetric or anti-symmetric eigenvalues under particle exchange. So there are simultaneous eigenstates which are either symmetric or anti-symmetric under particle exchange. And we've already seen examples of this when we were doing addition of angular momentum. So familiar examples. Suppose Suppose I had two identical particles, both with spin 1/2. Spin 1 is 1/2, together with another particle. Cross product with spin 2 equals 1/2. We know all possible addition of angular momentum for two spin 1/2 particles. And this gives us automatically, there were two possibilities, J equals 1 if I add the total angular momentum up in phase, and J equals 0 if you add it out of phase. And the two cases here, let me remind you the terminology. The J equals 1 is referred to as the spin triplet state. Why is it called a triplet? Because there are three states in the ladder with J equals 1. Jz equals +1, 0, and -1. J equals 0 is likewise called the spin singlet state. And maybe it wasn't super obvious before, but these two different states were symmetric or anti-symmetric under particle exchange automatically. We found for the spin triplets for each of those three states, the J equals 1, Jz equals +1 state, that was just both spins pointing up. Obviously, spin up and spin up is automatically identical under the exchange of which one is which. The J equals 1, Jz equals 0 state we obtained from lowering this state. And we got a combination that was symmetric, 1/√2 plus minus plus minus plus. This one is less trivial, but it is symmetric under exchange of which one is up and which one is down. And likewise, we trivially got J equals 1, Jz equals -1 was minus minus. So each of these states is symmetric under exchange. We found the singlet state by orthogonality. So it's no accident that since each of the J equals 1 triplet states was symmetric, the orthogonal combination was the anti-symmetric combination. So we found the J equals 0, Jz equals 0 state. The orthogonal combination 1/√2 plus minus 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 plus is the one which is anti-symmetric under exchange. So we will find when it comes to combining spin 1/2 particles that the total angular momentum, spin singlet or spin triplet, is a natural description of whether the state is going to be symmetric or anti-symmetric. These things are highly correlated with each other. Okay. Any questions? Everybody with me so far?
Can you explain what the notation you're using in the top right there actually means? What are you saying by that?
What this notation means, the
Yes.
direct product. Yes. So when I write 1/2 cross 1/2 equals 1 plus 0. This direct product means that I have a vector space made out of two totally independent subspaces. So my states are states psi1 and psi2, just like we were talking about before, where psi1 lives in the vector space of spin 1/2 particles. So this is the vector space of all psi plus, psi minus two component spinners. Psi2 itself lives in an identical copy of that space. Spin 1/2, this is its own psi plus, psi minus. So this cross product notation here means that this state, the two particle state, is separable into a single particle state in a particular vector space for the first guy, and independently specifying the single particle space for the second guy. So this is saying if the first particle lives in this vector space, which is the space of spin 1/2 particles, the second guy lives in a separate copy of the same space, that the combination of the two, the vector space that I make out of one guy from this space and one guy from that space, can be decomposed into one vector space of total angular momentum 1, and another independent vector space of total angular momentum 0. So this is a way of saying if I take any element psi1 from this space, x psi2 from this space, I don't know, let me put it this way. Psi1 1/2, psi2 1/2. How about this? Psi1 1/2 cross psi2 1/2 equals, there's one subspace that I get out of it of states with spin equals 1. And additively to that, there's a totally separate orthogonal space of spins 0. So, I don't know, I'm struggling with the language here. This is a larger vector space made up of multiplying two different vector spaces independently. And this is the algebraic statement that that combined vector space can be split up in a different basis into one subspace with a particular property and a different subspace which is orthogonal to it with a different property. But it's a statement here about combining vector spaces. Right, okay. Any other questions before we move on? Okay, so like I mentioned a little while ago, an actual proof of the spin statistics theorem requires relativistic quantum field theory because it involves sort of rotating space and time into each other. But the essence of it is the minus sign that shows up when you have a fermion or a spin 1/2 particle that you rotate and it generates a minus sign. So I want to give you a flavor of the spin statistics theorem. Proved using quantum field theory. The theorem is very simple to state, even though it's not so straightforward to prove. This is simply the correspondence that there is a link between the spin, so having integer spin versus half integer spin, maps 1-to-1 onto these statistics, which is the symmetry or anti-symmetry of the particles. Symmetry or anti-symmetry under exchange. So the bottom line is that particles with spin 1/2, 3/2, 5/2, any half integer spin are anti-symmetric. So when we say fermions, that implies both of these things, that it's a classification of their spin, and that's also equivalent to a classification of their statistics, that they follow Fermi-Dirac statistics. And then likewise, the integer spin particles, spin 0, spin 1, spin 2, integer spin, are always symmetric under exchange. And so when we say that these are bosons, that means both that we are specifying their spin and also that we are specifying that they satisfy Bose-Einstein statistics. Which is just the consequence of the wave function always being symmetric under exchange. So, okay, where does this come from? Very loosely speaking. Suppose I look at a matrix element, which involves two particles. And for the sake of argument, let me suppose I take one of them and I rotate its spin by a factor of pi. Psi of r, e to the minus I over h bar, s dot pi n times psi of negative r. So exactly what this means is a little bit beyond the scope of this course. These really aren't wave functions. These are quantum field operators. And I'm rotating the quantum field. You can think of it like a wave function. This is the rotation operator that rotates the spin by an angle of pi, about some axis tan. So I write U dagger and U. This one is evaluated at a particular position R. This one is evaluated at a particular position minus R. So suppose for the sake of argument, I start off with this correlator. And I ask, what happens if I take the whole thing, the space and the spin, and I rotate it by a factor of pi? Rotate everything, spin and orbital, by a factor of pi in that direction. And the statement is, this object should be invariant under that rotation. This should be a scalar object, and it shouldn't change if I rotate it. It should be invariant. So what do I get if I do that? So under that transformation, this thing is supposed to be equal to another rotation by pi. So I have U dagger on the left. So I get e to the plus I over h bar s dot pi n from the spin part. I have e to the plus I over h bar L dot pi n. And then this is hitting the thing that I started off with. E to the plus I over h bar s dot pi n psi of r, e to the minus I over h bar s dot pi n psi of negative r. And then on the right-hand side, I'm multiplying by the adjoint of this. So I get e to the minus I over h bar L dot pi n e to the minus I over h bar s dot pi n. So these are all operators. So all I've done is I've taken this object and I've hit it from the left with the rotation operator U dagger, and on the right by the rotation operator U, where I'm rotating both the orbital part with L and I'm rotating the spin part with S. So what's it going to do? Strictly speaking, to be able to decide how these operators transform, I've got to insert something in between. I've got to have something over here. Right? I have some rotation operator on the left and a rotation operator on the right. So let me, for instance, put in e to the minus I over h bar L dot pi n, and also its opposite, e to the plus I over h bar L dot pi n. These guys are inverses of each other. I can put them in for free. And now what I have looks like this is a spatial rotation by angle pi, which is going to rotate the position vector r of this thing by pi radians. Likewise, this looks like a rotation operator acting on this thing, which is going to rotate its spatial position by a factor of pi radians. So all that does is that turns psi of r into psi of minus r. I swap the position because I rotated space by pi radians. And it's going to turn psi of negative r into psi of positive. Okay, so far so good. I rotated space, and I still haven't dealt with what's going on in the spin. But I'm in luck, right? So I have e to the I over h bar s dot pi, another e to the I over h bar s dot pi. Those add up together. It's the same operator. So what I'm left with is e to the plus I over h bar s dot 2 pi. I rotated space, so now I get psi of negative r. That's now sitting next to psi of positive r. And then I have, in between, there's one more spin operator, e to the minus I over h bar s dot pi n, psi of positive r, and then I have e to the minus I over h bar s dot pi. So I've taken care of the spatial rotation part. Now I'm just looking at the spin rotation part. This is what I'm looking for here. This is the object that takes the spin information and rotates it by 2 pi radians. This is the part that's going to give me a minus sign if this is a fermion, and it's going to give me a positive sign if it's a boson. To put it in the right form, again, I've got to insert something in between. So it looks like U dagger on the left, the same U on the right. So all I really need to do is I need to add and subtract the factor of pi here. So I'm going to write this thing as e to the minus I over h bar s dot 2 pi n times e to the plus I over h bar s dot pi. Obviously, negative 2 pi and positive pi gives me negative pi, so this is legal. And when I do that, this is the spin rotation operator by 2 pi on the right. This is U dagger on the left. That's going to rotate the spin of this thing by 2 pi. Now's the part where I invoke that minus sign. So if the field psi of r is a fermion, meaning spin 1/2 or 3/2, some half integer spin, then that means when I have this rotation operator, e to the plus I over h bar s dot 2 pi n psi of r, I'm just rotating the spin parts. For a spin 1/2 particle, this thing changes sign when you rotate its spin by 360 degrees. On the other hand, if it's a boson, then it doesn't change sign. It comes back to the positive. And 0, 1, or so on. Then that rotation operator gives me e to the plus I over h bar s dot 2 pi n psi of r, e to the minus I over h bar s dot 2 pi n. This gives me plus psi of r. So depending on the spin of the particle and how it transforms under a rotation, that determines what this correlation function gives me. So either way, I'm going to get plus or minus, and then I'm going to get the same state back, psi of negative r. And then I'm left with the spin rotated thing on the right, e to the minus I over h bar s dot pi n psi of negative r e to the plus I over h bar s dot pi. This is supposed to be equal to the thing that I started off with. So this is equal to the rotated thing on the left. Oh, I think I already swapped my plus and minus here, excuse me. E to the plus I over h bar s dot pi n psi of, and then this one is the positive. Psi of r e to the minus I over h bar s dot pi n psi of negative 1. So this is sort of the punchline of the proof, if you can call it that. What I've done is I've applied a rotation to this thing. And that rotation has generated a plus or a minus, depending on how the spin transformed under that 2 pi rotation. The other thing that I've done is I've effectively commuted these objects past each other. I have psi of negative r, and then this thing, which is a rotation of the spin of psi of r. After this transformation, the rotated thing is on the left, and psi of r is on the right. Psi of negative r is on the right. So from the properties of rotation, which is where the minus sign comes from, we learned something about the commutation relations of the fields. So the crux of where this comes from is that the rotational properties imply the commutator algebra. So now, suppose I drop this spin rotation, right? So I just redefine which spin I'm talking about for this field. This is telling me that if the fields are fermions, they anti-commute with each other. If the fields are bosons, they commute with each other. So for fermions, that tells me psi of r, psi of negative r is negative psi of negative r, psi of r. When I commute the fields past each other, which is equivalent to swapping which particle is at which location, I get a minus sign, anti-symmetric under exchange. On the other hand, if they are bosons, I get a plus sign. Psi of negative r, psi of positive r is plus psi of positive r, psi of negative r. So this is symmetric under exchange. So this is, like I said, a bit beyond the scope of what we know how to manipulate in this class. But the essence of it is something that we've already seen before. It's this rotational property. And the implication of a rotational property is that that tells you whether the particles are even or odd under exchange. To do this for real, you need relativity because this is a rotation in space and in time. So the same general statement is true about how spins rotate, but you need to broaden the notion of what rotation means to include a rotation of 4-dimensional space-time and not just 3-dimensional space. It's interesting to note that Richard Feynman in his Feynman lecture said, it seems like we don't really understand the fundamental principle behind the spin statistics theorem because it's so easy to state, but so complicated to prove that there's got to be some underlying principle that we haven't fully put our finger on yet. So the punchline from all of this, the conclusion is that for spin 1/2, 3 halves, etc., half integer spin. These are fermions, and they are anti-symmetric always. That is linked to their spin by rotational symmetry. And spin 0, spin 1, spin 2, these are bosons, and they are always symmetric. I say always, but there's a dimensionality caveat here, which is actually pretty cool. This is true. The spin statistics theorem is valid in 3 dimensions, 3 spatial dimensions. It may be valid in more, I'm not sure. It's definitely valid in 3 dimensions. I'm not sure the implications, maybe more. But it's kind of cool because it breaks in fewer dimensions. And this is the origin of some really weird stuff in condensed matter. If you artificially create a 2-dimensional surface, like an interface between one material and another one where you have a confined electron gas, you can violate the spin statistics theorem in 2 dimensions just fine. And then you can create particles that have really weird statistics. Those are referred to as anyons. So these guys don't have explicit symmetry with +1 or -1. They can transform by an arbitrary complex phase. So under rotations, let's say under exchange, phi of psi1, psi2 will be e to the I theta, psi2, psi1. This is the kind of thing that's only possible in low-dimensional physics like 2D. But you can do some really neat things, and these phases are associated with topological effects like braiding and winding number based on how you twist them around each other when you exchange. Condensed matter can do neat stuff like that. Okay. Now that we've talked about where this effect comes from, what do you actually do with it? At the end of the day, the thing that you will need to be able to do under pressure is to impose this requirement about symmetry or anti-symmetry on other problems you're already solving. So one implication of this is that depending on the spin state of 2 electrons, 2 fermions, their orbital state may need to be symmetric or anti-symmetric. in order to guarantee that the total wave function, including both spin and orbital degrees of freedom, is overall antisymmetric as required. So this is the symmetry property, let me emphasize here, under total exchange of everything, including both spin states and orbital states. So for instance, suppose I have two electrons that are in a spin singlet state. The spin singlet state, we said, was the J equals 0, JZ equals 0 combination. This was 1 over root 2 plus minus 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 plus. If I tell you that they're in a spin singlet state, then I have told you that their spin degrees of freedom are already antisymmetric.
Is this like,
go ahead.
Are like you telling us the spin degrees of freedom are antisymmetric? Is that like a given for the problem, or is that a given because you already said they're
so we'll go
electrons?
through some examples from previous year's comprehensive exams in a minute, and it'll say things like, if you have two electrons in a spin singlet state, what levels of the harmonic oscillator can they be? So they'll tell you, if the spin information is this, then what do I know about the orbital information? Or if I know something about the orbital information, what do I know about the spin? Or here's an example of both the spin and the orbital. Is it allowed or not? Those are the kind of questions you'll have to answer. So if I treat this as a given, the question will be, what kind of orbital states can they be in? In this example, if the spin is antisymmetric because they're in a spin singlet state, then this means that the orbital state will need to be symmetric. Right, so the requirement is that when I swap everything, that there should be a minus sign change. The spin is already giving me a minus sign. I don't want another minus sign to show up from the orbital part, then I would get a plus sign. So for example, this means that they could both particles be in the ground state of the same harmonic oscillator. Both be ground states n equals 0 of a harmonic oscillator. So a valid state for two electrons that satisfies their antisymmetry requirement would be something like a spin singlet state, J equals 0, JZ equals 0, and an orbital state, let's say N1 equals 0 and N2 equals 0. It doesn't necessarily look like this thing is antisymmetric when written this way in terms of total J. But if I write this out in terms of the individual spin states, so this is 1 over root 2. The first particle is in a quantum state N1 equals 0 and its spin state is plus. The second particle is in a state N2 is equal to 0 and its spin state is minus. Minus 1 over root 2. Same orbital state, N1 equals 0, but now its spin is minus, N2 equals 0, and its spin state is plus. So the point of all of this is, if the spin stuff is already antisymmetric, you want the orbital part to be symmetric so that the combination of the two, when I exchange everything, what n value it is and what spin, then I get that relative minus sign in between. So the thing has to overall be antisymmetric. And that means either the spin part needs to be antisymmetric or the orbital part needs to be antisymmetric, but not both. If you change minus sign 2 times, then you end up with a plus sign, and that would violate the antisymmetry requirement. So for 2 electrons in a spin singlet state, they are perfectly happy to be in the same quantum state or a symmetric combination of quantum states. they would not be allowed to be in an antisymmetric combination. On the other hand, if the electrons were in a spin triplet state, doesn't really matter which one because all of the triplet states are even under exchange. So that state could be plus plus, it could be minus minus, it could be plus minus, plus minus, plus over root 2. In any of these cases, their spin part is symmetric. So you've got to get a minus sign. The minus sign is not coming from the spin stuff. So the minus sign must come from the orbital parts. Must be antisymmetric. So part of what that means is they cannot both be in the same quantum state. You cannot have n equals 0 and 2 equals 0. This is symmetric. This part is also symmetric. That would violate their statistics. So this is essentially the Pauli exclusion principle. The anti-symmetry requirement says that they cannot have identical quantum numbers. If they had identical quantum numbers, they would be even under exchange. And that violates the spin statistics theorem. So cannot be in identical quantum states. Same spin, same orbital state. But no, so this is the Pauli exclusion principle. But note that the symmetry condition is more general than just the Pauli exclusion principle. You can look at these combinations and say, okay, if they're both in spin plus, they can't both be in the ground state n equals 0. Pauli exclusion is not going to tell you that this state is forbidden. I have a symmetric combination of plus minus and minus plus. Here I've got different spins. This does not appear to violate the usual way we talk about the Pauli exclusion principle, but it still violates their spin statistics because this is a symmetric combination of their spins. So in this example, if the particles are in a spin triplet state, they have to be in different quantum states orbitally. And they have to be in an anti-symmetric combination of those orbital states. So if they are in a spin triplet state, a valid orbital state would be a linear combination of n equals 0 and n equals 1. But I can't just write down 0, 1. That is not symmetric nor anti-symmetric under exchange. I've got to make the combination that is anti-symmetric. So I could have an orbital state which is 1 over root 2 n1 equals 0, n2 equals 1, minus n1 equals 1, n2 equals 0. You see what I mean? I can't just say, oh, I put them in different quantum states, so I'm good with Pauli. No, it needs to be anti-symmetric under exchange. So they have to be in different quantum states, and you have to assemble the combination of them that is odd under exchange. When I put these two things together, the total state would be something like, let's see, so this would, let's say the J equals 1, JZ equals plus 1 state, and then an anti-symmetric combination of 0 and 1. I don't know, let me note this as 0, 1, anti-symmetric. Or what I mean by this is exactly this combination. 1 over root 2, this is the state, and 1 equals 0 is spin up, and 2 equals 1 also is spin up, minus, and 1 equals 1 with spin up, and 2 equals 0 also with spin up. This object is anti-symmetric under total exchange of all quantum numbers. If I swap n equals 1, n equals 0 plus, I generate a relative minus sign, as I'm supposed to be good with Fermi. So the point of all of this is the symmetry requirements come in at the level of both the spin and the orbital stuff. So two electrons can have the same spin, but then they have to be in an antisymmetric orbital combination. If they have different spins in an antisymmetric combination, then they are allowed to be in the same quantum state and they must be in a symmetric combination state. So this is the main application that you will need to use under pressure. Any questions on this before we go to some examples from the comprehensive exam?
At first, we were looking at them both being in the ground state, so it's N1 equals 0 and N2 equals 0.
Yes.
And then, so obviously they can be in the same state, and then we immediately went from 0 to 1. Does it need to be like 1? Is there a chance that it could go to N equals 2 and have
Yeah, it doesn't matter
combination of that?
State is here. This could be 7, it could be 45, it doesn't matter. The thing that does matter is that you have to explicitly anti-symmetrize which one is in which state.
Okay.
The point here was that they cannot be in the same state because the same state is always symmetric. And it's also not enough just to put down one of them is in one state, one of them is in a different state. That is still not anti-symmetric. You've got to have them in different states and you've got to anti-symmetrize the difference. Is that clear?
Yes.
Okay. All right, so let's look at some examples of things that you will do under pressure. All right, so this is an example from the 2018 comprehensive exam. Number 4A, the link is in the notes. So you are given an example for two spin 1/2 particles in one dimension. Is the following an allowed wave function? Is this allowed? And you have psi spin 1, spin 2 of x1 and x2, which is some normalization factor nobody cares about. X1 minus x2 e to the minus x1 minus x2 squared. And then the state is up, down, minus, down, up. So is this state consistent or inconsistent with the statistics of spin 1/2 particles? Any thoughts? What happens to the spin stuff if I exchange the particles? Is it even or odd? Odd. The spin information is odd, anti-symmetric under exchange.
But we have the minus sign in the right away, right?
Bingo. So this is the trick of this question. The spin part looks nice and anti-symmetric. If you look at that, then you'll say, yes, I'm good. But you have to consider the totality of the wave function. It is anti-symmetric under the spin degrees of freedom, but because of this factor, it is also anti-symmetric under the orbital. So this is not going to be allowed. So you will see if you swap them both, if I have psi of S2, S1 with arguments X2 and X1, I swap the location of the particles and I swap which spin they have. I generate one minus sign from swapping this. I generate another minus sign from swapping that. And under exchange, this wave function combination is actually even. So the answer is no. It violates Fermi-Dirac statistics.
Because we know that half integer spins are supposed to be odd, and or because we know 1/2 spin 1/2 states are supposed to be negative.
That's correct.
Okay.
So you have to redefine what you mean by up and down. But if these were spin 1 particles, on the other hand, and let's say this was spin +1, spin -1, spin -1, spin +1. If these were spin 1 particles, this is a perfectly good bosonic state. Everybody with me? Okay. Another little detail that makes it a bit easier to work with the two-particle symmetrization is if you're dealing with two particles that are interacting in a central potential with each other, right? So you have the two-body problem. for two identical particles in a two-body potential, i.e. a central potential. So I have something like Hamiltonian is P1 squared, P1 hat squared over 2M1, P2 squared over 2M2 plus some potential that depends on R1 minus R2. I don't care whether it's spherically symmetric or not. All I care about is the fact that it only depends on the difference R1 and R2. We already know that for a problem like this, you solved it last semester, you've also solved it this semester, that it's advantageous to go to center of mass and relative coordinates. To center of mass and relative coordinates. We know that this Hamiltonian can be written as total momentum p squared over 2 times total mass plus relative momentum p squared over 2 times the reduced mass plus relative potential V of R, where capital M is little m1 plus m2, mu is the reduced mass m1, m2 over m1 plus m2. Capital P is the total momentum, which is conserved, P1 plus P2. Little p is the relative momentum, P1 minus P2. And this R is the relative distance R1 minus R2. So this is the case you encounter all the time. What does symmetry look like in this case? You'll actually be solving the Schrodinger equation. Time-independent Schrodinger equation will look like minus h bar squared over 2 mu, Laplacian plus V of R, psi of R equals P psi of R. So the key here is that in relative coordinates, exchange of the particles is swapping R1 and R2. That corresponds to taking R to negative R. So in relative coordinates, particle exchange really just looks like, is it an even function or an odd function of R? R goes to negative R. Even function of R versus odd function of R. So when you look at the spin state and you look at the orbital state, you'll compare, is the spin state symmetric or anti-symmetric, and is this relative coordinate R dependence an even function or an odd function? So let's go to another example. This is an example from last year's comprehensive exam. 2019, number 5D. You're given two identical particles both of mass m, and they are sitting in a relative potential V of x1 and x2 in one dimension is like a square well. It's equal to 0 if x1 minus x2 is less than L over 2. And it's equal to infinity. X1 minus x2 is greater than L over 2. So this obviously looks a lot like the infinite square well. In terms of these relative coordinates, V of x versus x, where x, the relative coordinate, is x1 minus x2. At L over 2, the potential jumps up to infinity. At minus L over 2, the potential jumps up to infinity. In between, it's 0. This is the familiar square well. And so for two identical particles, okay, I guess it doesn't say at first that they are identical. It asks you two different cases. So first, what is the ground state if the particles are distinguishable? And then what is the ground state if they are indistinguishable spin 1/2 particles with spins parallel? is the ground state energy if they are distinguishable. If they're distinguishable, then that means that the particle exchange does not have to be a symmetry of the Hamiltonian. They don't have to have any particular properties one way or the other under symmetry or anti-symmetry. So we already know what the ground state solution of the square well potential is. Right? The ground state is the one that looks like this. The wave function goes to 0 at the endpoints, and it oscillates like a plane wave in between. The energy of the ground state is the energy of a free particle with the appropriate wavelength. H bar squared k squared over 2m. And the quantization condition just comes from the wave number needing to fit inside the square hole. It's got to go to 0 here and here in 1/2 wavelength. So this was the condition n pi over L. And if you sit and think for a minute, is it going to be sine or cosine? Well, if this is an even function around x equals 0, it's got to be cosine. So the ground state psi 0 of x is going to be some normalization that I don't particularly care about, cosine pi over Lx. And I say, okay, sanity check, sorry, not n equals 0, n equals 1. Sanity check when x is L over 2, I get cosine pi over 2, which goes to 0 the way it's supposed to. So this endpoint works. If L is negative pi over 2, it also goes to 0. So this is the correct solution. I should also remember that the mass here is the reduced mass, mu, not the mass m of the two particles that I was given. Otherwise, I'll be off by a factor of 2. So in this case, the energy is h bar squared over 2. The reduced mass is 1/2 of the regular mass, since it is two particles that are identical to each other. And then this wavelength is pi over L squared. So my answer is h bar squared pi squared over ml squared for the distinguishable case that I don't have to worry about statistics and symmetry or anti-symmetry. On the other hand, what is the ground state energy if they are spin 1/2 particles with spin parallel? Spin 1/2 particles with spins parallel, i.e. something like plus plus. If the spin degrees of freedom are symmetric, then I must demand that the orbital state be anti-symmetric. Anti-symmetric meaning odd if I exchange x1 and x2. In this relative coordinate, that means it's an odd function of x. And this is where the answer changes from before. It cannot be in the ground state of this well because this wave function is an even function. This is even under the exchange of which one is over here and which one is over there. I need to go to the next excited state, the n equals 1 state. X d of x, that ground state is forbidden by statistics. So now I have to go to the next excited state, which is now anti-symmetric under r goes to minus r. So this requirement means that I cannot be in the even ground state n equals 1. Did I hear a question?
Yes. So if the orbital state must be antisymmetric, doesn't that mean that one of the particles can be in the ground state then? One can be in the ground state, but then one needs to be in the n equals 2 state?
The language is a little bit deceptive here. There's not one particle in one state, one particle in another state. This is the system in a relative coordinate that is in one state or the other. So that's what I want to emphasize here. This is not particle number 1 sitting in the ground state, particle number 2 sitting in the excited state. This is a property of both particles together, the relative motion coming from the relative coordinate Schrodinger equation is even or odd. Does that make sense? The question has changed. It's not like which particle is in which quantum state. The system collectively is in either a symmetric or anti-symmetric ground state.
Okay.
Does that help?
Yeah.
Okay.
So when we say that the particles are distinguishable, even if they were to have, half integer spin, then the spin statistics theorem doesn't apply.
That's right. Yeah. So if one of them is a spin 1/2 electron, the other is a spin 1/2 muon, then that means that they've got different quantum numbers that I can tell them apart, and they do not have to have any particular symmetry among them. So the answer in this case is I have to go to the next excited state. This wave function will look like sine of 2 pi over L. So my psi 2 of x will look like sine 2 pi over Lx. And my wave number Kn will now be 2 pi over L, which means my energy is h bar squared over 2 mu, 2 pi over L squared. This is the same thing that I had before, but it's bigger by a factor of 4. So when I crunch the numbers, I get 4 h bar squared pi squared over mL squared. So this is 4 times higher because of the statistics. Any questions on this example?
Back to the distinguishable thing.
Yes.
You had the electron and the muon, for example, that each one would have to follow individually this spin statistics theorem with their own.
Yes, with other particles of their kind. So yeah, if I've got 2 muons and 1 electron, the muons have to be anti-symmetrized under exchange. The electron is doing its own thing. If I've got 2 muons and 2 electrons, then these are anti-symmetric. These guys are anti-symmetric, but they don't have to do anything particular with respect to each other. Okay, we are almost out of time, so let me flash another example for you instead of doing it on the board. Let me share screen now. Okay, so a similar example. All right, so we did this example, we did this example, similar example for the harmonic oscillator. Here, instead of being trapped in an infinite square well, here you've got a relative potential, which is the harmonic oscillator potential. Same basic idea. 2 identical spin 1/2 particles, both of them with spin up. And so that means you already know what the energy levels of the harmonic oscillator are, but the statistics forbid them from being in that relative ground state. So instead, they must be in the first excited state, n equals 1. And the only other thing to remember here is that this was the harmonic oscillator in 3 dimensions. So that 0-point energy is 3 halves because you've got 1 half each for x, y, and z. So the ground state energy of this thing would be 5 halves h bar omega because of the statistics. Okay, there's lots more that could be said. We've talked about the implications for the Pauli exclusion principle. In general, the interaction for symmetry and anti-symmetry of wave functions leads to an effective force or an effective energy of the interaction between 2 identical particles. So if I have 2 wave functions, so say I've just got 3 particles, and I start off with 2 wave functions that are localized. If they add symmetrically, so if these are bosons, for instance, then the wave functions will be symmetric. In that case, when I add the overlapping Gaussians, I get something which is really smooth in the middle. That smooth wave function accumulates the probability in between. This starts to look like a covalent bond between 2 atoms. It also means that since the wave function flattens out, the derivative gets smaller. The derivative of the wave function is related to the kinetic energy. So this flattening with a bonding state with energy in between actually has lower energy. It is more stable because it reduces the amount of kinetic energy of the particles. On the other hand, if the orbital wave function is demanded to be anti-symmetric, then I've got a swap between a peak on one side and a valley on the other. This forces a node where the wave function together has to go through 0. That does the opposite. That depletes probability in the middle and it concentrates them opposite to each other. And it raises the kinetic energy because you've got a high gradient in between. So this actually raises the energy. It acts like a repulsive interaction between them. So these features are known as the Pauli pressure, the effective repulsive force that happens when you have 2 wave functions that are spatially anti-symmetric. They cannot be squeezed together. The harder you squeeze them together, the more the wave function pushes them apart. So in quantum statistical mechanics, this is the origin of Fermi-Dirac statistics, that if you try to squeeze a bunch of states together, At t equals 0, they start to fill up independent quantum states until you form the Fermi sphere with a Fermi energy depending on the number of particles that you have in the system. On the other hand, if you have bosons, when you squeeze them together, the tighter they get, the more attractive a force they be. That's what leads ultimately to Bose condensation and the formation of Bose-Einstein condensate in quantum statistical mechanics. Okay, there's a lot more that can be said about how to generalize this to n particles, but I think I'm going to have to stop here. Let me ask you guys, have you guys encountered any of this discussion about the quantum ideal gaps in your statistical mechanics class? You have, okay. So hopefully this is a little bit familiar there when you talk about the occupation number of fermions being 0 or 1, the occupation of bosons can be up to infinity, and that leads to that effective quantum pressure of the otherwise non-interacting gas. Okay, any other questions or concerns before we adjourn for the week? All right, thank you guys very much. Have a nice weekend. Keep an eye out for the take-home midterm that will appear on Friday.
You have time for a fun question.
Yeah, absolutely.
So I asked this